All right, let's talk about something I'm sure you've run into. You're staring at two totally different clustering results from the exact same data, and you're just wondering, which one do I trust? Well, if that sounds familiar, then you're in the right place. We're going to dive into a really powerful technique that helps you find a single, much more reliable answer by combining lots of different solutions into one.
So here's the game plan. First, we're going to unpack what makes clustering so tricky in the first place, that core problem. Then we'll introduce the solution, our hero for today, the cluster ensemble. We'll get into how they're built, look at the two big ideas behind them, and then, to wrap it all up, we'll go through a practical guide so you can pick the right approach for your own projects.
Okay, let's just dive right in. I mean, to really get why cluster ensembles are such a big deal, we first have to talk about a headache that, let's be honest, every single one of us in data has faced, just how ambiguous clustering can be. You know the drill, right? You run k-means, you get one set of clusters. Cool. Then you run, say, a hierarchical algorithm on that same data, and you get a totally different set of groupings. And the frustrating part is they both look pretty plausible. So what now? Which one's the real structure of your data? How can you possibly be confident in what you're presenting? And here's the tough pill to swallow. There's just no silver bullet here. Nope. Every single clustering algorithm brings its own baggage, its own biases, its own assumptions about what a good cluster looks like. And since we're usually working with unsupervised data, there's no ground truth to check our work against. So we're left juggling multiple plausible answers. It's ambiguous, to say the least. Okay, so if we know that any one algorithm might lead us astray, what's the alternative? Well, what if instead of relying on one opinion, we could get a much better, more stable answer by combining lots of them? This, my friends, is where the whole idea of the ensemble comes into play. Think of it like the wisdom of the crowd. And that's the absolute core of a clustering ensemble. You'll sometimes hear it called clustering aggregation, but the concept is the same. It's like, instead of trusting a single expert's opinion, you're going to pull a whole room full of them. We're going to generate a bunch of different ways to cluster the data, and then figure out a smart way to combine all of their votes into one final, unified result. So why go through all this effort? Is it worth it? Oh, absolutely. Because a good ensemble gives you a result that's just better. It's more robust, it's more stable than what any single algorithm could ever hope to achieve by itself. It's way better at handling noisy data, it doesn't get thrown off by outliers as easily, and this is the really cool part, it can sometimes find complex structures in the data that any one method would have just completely missed.
All right, so how does this all actually work under the hood? Well, it's actually a pretty elegant two-step process, and once you get these two steps, you basically understand the foundation of every cluster ensemble method out there.
Yeah, every single one follows this pattern. Step 1 is generation. This is where you go out and create a really diverse set of different clustering solutions. Then comes step 2, the consensus function. This is where you take all those different solutions and combine them to get your final answer. It's a really powerful 1-2 punch. First, generate diversity, then find the consensus.
And the cool thing is, there are a ton of ways to generate that diversity. You can throw different algorithms at it, k-means, spectral, whatever. You can use the same algorithm, but just play with the parameters. You can sample different subsets of your features or your data points. You can even project the data into totally different spaces. The big idea here, the really key takeaway, is that the more varied and diverse your starting clusterings are, the more raw material your consensus function has to build a truly solid final result. Okay, so we've generated our big, diverse collection of clusterings. Now comes the really critical part. This is where the different ensemble methods start to show their true colors. How in the world do you actually combine all of them to find a single consensus? Well, it turns out there are two main schools of thought here. The first is called objects co-occurrence. You can think of this as a bottom-up, voting-based method. It's asking a really simple question. If we pick any two data points, how often did they land in the same cluster together across all of our attempts? Then you have the second approach, the median partition. This one's more of a top-down optimization problem. It asks, can we mathematically find one single central partition that is the best compromise between all of the different ones we generated? The co-association matrix is just a brilliant way to visualize that first approach. What you're doing is taking your whole ensemble of results and basically melting them down into a brand new similarity matrix. It's so clever. Every cell in this new matrix tells you the percentage of times that two specific points were clustered together. It's like a democratic vote on how similar any two points are. And the best part? You can then just run a final clustering algorithm on this new super-informed similarity matrix to get your consensus.
Now, that second approach, the median partition, well, that's a much tougher nut to crack. I mean, the idea is really elegant, right? Let's just find the single best partition that represents the center of all the others. But in reality, it's computationally a nightmare. As you see here, the problem is what we call NP-hard. And all that really means is that finding the perfect exact solution is basically impossible for any dataset that's not trivially small. So what do? We have to rely on smart shortcuts, heuristics, and approximations to find a solution that's good enough. So there you have it, two really different ways of thinking about consensus. And as you can imagine, this has led to a whole bunch of different algorithms, which of course brings us to the million-dollar question for any practitioner. Okay, which one should I actually use?
Well, this table really lays out the trade-offs. If you look at the co-occurrence family, the classic co-association matrix is simple to grasp, but it can be really slow, computationally heavy. That's why people develop smarter graph-based methods like HGPA and MCLA. These are incredibly popular because they're fast. We're talking nearly linear time in some cases. Then you've got the other camp, the median partition methods. These are more theoretically pure, but you're always dealing with that heuristic-dependent cost. Their performance really hinges on the cleverness of the approximation you're using.
So when it comes right down to it, your choice really depends on what you need. Are you working with a massive data set? Is speed your #1 priority? Then you should absolutely be looking at a graph-based method from that co-occurrence family. It's probably your best bet. But if you need something that's more theoretically sound, or maybe you need the kind of flexibility that kernel methods can offer, then it might be worth diving into the extra complexity of the median partition approaches. And that kind of brings us to a final thought to leave you with. Look, we've seen that cluster ensembles are a fantastic tool for getting results you can actually trust. But this field is far from finished. Researchers are already pushing the boundaries, asking some really interesting questions. Like, what if the clusters overlap? How do you combine those? Or, hey, what if we could use the original data itself to help us find a smarter consensus? These are the kinds of questions that are driving the future of this field, and it's going to be really exciting to see what comes next.